Formation of the elements and distribution in the Earth, and never forget about the element of surprise, which is between something called RF. It's just right underneath tantalum, which is a new one for me. All right, we want to know what the bulk composition of the Earth is and how the elements are partitioned between the different layers. Where are the elements we need? Well, they better be near the surface, because otherwise we're not getting to them, as we'll see. So let's start with how the elements form. They were not all present at the beginning, and in fact, the elements have evolved with time. So when the universe started 13.8 billion years ago, there were no atoms. So the early universe was too hot for electrons to remain bound to atoms. The first elements, hydrogen and helium, couldn't form until the universe had cooled enough to allow their nuclei to capture electrons, as we can see there on the right. So here we have sort of nucleon and electron soup, and over here we start to form atoms. There might have been a small amount of beryllium, but I think it was nearly all hydrogen and helium. So the rest of the periodic table formed since then. So where did the other 88 elements come from? Let's watch a video.
You've almost certainly seen a periodic table of the elements, but have you ever wondered where those elements came from? To understand their origin, first we have to look at what defines an element. An atom is made up of positively charged protons and neutral neutrons in a nucleus, surrounded by negatively charged electrons. The number of protons in the nucleus defines an element, but a single element may have atoms with a varying number of neutrons. These are called isotopes, and though these are all still the same element, they vary in their stability. Some nuclei are stable and require large amounts of energy or bombardment by other particles to transform into different elements or isotopes. Other nuclei are inherently unstable and will spontaneously decay. We begin our story with the Big Bang. As the universe expanded and cooled, the sea of fundamental particles began to coalesce, forming the first protons. And a proton is the nucleus of the first element on the periodic table, hydrogen. In the first few minutes, a few more nuclear reactions occurred to create some helium and very tiny amounts of lithium. At this point, synthesis of larger elements was put on hold, until the inhomogeneity of the universe led to the formation of stars, which could become hot enough to allow for further reactions. Many stars start off small, and are fueled by their ability to fuse hydrogen into helium, much like our own sun. Once their hydrogen fuel has been used up, stars which are massive enough go on to fuse together larger elements, while they themselves increase in size and temperature. But there is a limit to a star's ability to fuse smaller elements into larger ones. When small nuclei are fused together, the nuclear reaction releases energy, supplying the pressure needed to keep a large star from collapsing onto itself. But we reach a problem when a star forms iron-56. The nucleus of this isotope of iron is the most stable nucleus in nature, meaning that it can't be fused further to fuel a star. In other words, stellar nucleosynthesis halts at iron. At this point, the star has no energy to overcome gravity, causing it to implode and then rebound to explode in what we call a supernova. During a supernova, intense amounts of heat and gamma rays are produced. These gamma rays go on to break apart some iron nuclei into, among other things, copious amounts of neutrons. Intact iron then acts as a seed, capturing these neutrons and then decaying into new, heavier elements. Some of these new elements can even undergo nuclear fission to produce other ones. This process in a supernova is the primary one responsible for creating every element past iron, all the way up to plutonium. And since it is an explosion, all of these atoms are sent flying throughout the universe. But that still leaves a few more elements. Backtracking a bit, lithium, beryllium, and boron are not made in large quantities in stars. That's because these elements tend to be used up almost as soon as they are synthesized. Instead, they're made primarily by cosmic ray spallation, a process where high-energy particles collide with carbon, nitrogen, and oxygen, removing nucleons to yield these three smaller elements. And finally, every element larger than plutonium was made synthetically by scientists, though plutonium itself and a few smaller ones can also be man-made. In the end, all of these processes are responsible for creating every atom in the universe, including the ones that make up you and me and the entire Earth we live on. Now, understanding stellar life cycles and nuclear processes can be very complex, and this video just touched on the basics. If you're interested in learning more, feel free to ask questions below or check out some of the links included in the description. Check out Everyday Elements on Facebook, and above all, be sure to subscribe.
Okay, now, this diagram is the scientific representation of what he just said. So we haven't talked about what binding energy is per nucleon, but the fact is that if you combine two hydrogens, you generate a helium, and the binding energy is greater than the heliums that went together to make it. So that energy is released to make the stars glow, and that gets you up to iron, as he pointed out. So you can get up to iron in the core of certain stars, but you can't get beyond that because the binding energy per nucleon is lower than that of iron. So you can't generate more of these and drive fusion in the core of a star. Instead, you have to go through a supernova. So the way to think about this thing is, here we got hydrogen and helium. They were sort of present very quickly after the Big Bang. You know, he talked about boron, beryllium, and lithium as something that forms in a special way by galactic rays. And then everything else up to iron, including iron, happens in the bellies of stars. And then everything over here, that forms as a result of supernova and related phenomena. Okay? That's how you form the elements. And then they all obviously get mixed up, and we end up with something like the Earth. All right, so this Tom, you've got a question.
Sorry, it might be a silly question, but I was just wondering why it stops at iron. Like, why 56?
So the nucleosynthetic reasons, you know, I think we're talking about astrophysics or something here, which is way beyond my ken.
Okay.
But the observation is that the binding energy per nucleon reaches a maximum at iron. So for whatever quantum mechanical reason that happens, I'll be honest with you. When I started my graduate education at UC San Diego, I thought I'd take a course in quantum mechanics. So I went to one lecture, and it was like, okay, that's enough. I didn't understand a single thing that the professor said, and I dropped that course immediately because it's just too theoretical. I'm a geologist. There's a reason. But that's so important because iron is a very common metal. As we've seen, it is the most common metal, and it is the most important metal. If you said, what one metal can we absolutely not do without, it would be iron. And so it's quite fortuitous, isn't it, that the one thing that stars are really happy making for us is iron, and if we want anything beyond iron, we have to wait for it to go through some kind of a drama, like blow up, make a supernova. So that's by way of admitting that I didn't give you a very good answer. But the least I can do, if you ask a good question, is try and be entertaining. So when I try and be entertaining, that's basically me saying, gee, I wish I had an answer for you. So
Thanks.
thank you. Questions they make this class fun, in my opinion. All right, so this is a sort of a summary, you know, a little confusing. Periodic table, where do the elements come from? There we got the Big Bang up on top, no problem. Cosmic rays, that's lithium, beryllium, boron. large stars, small stars, carbon, nitrogen, oxygen. You can't get any fluorine, sodium, up to iron from small stars, so it's all kind of green. Oh, wait a minute, there's neon, so you can get that. Oh, there's oxygen. But oh, wait a minute, there's sulfur. They can get that from small stars. So large stars. Now look at the supernova. Now the supernova, as I said, everything beyond that. Now this is confusing to me because it says you can get copper and zinc from large stars, not supernova. So I'm a little confused. But and arsenic. Yes, Clint, maybe do you have an explanation for my puzzlement?
No, but I used that very version for some time back in the teens, and then heard about there are even other sources of heavier elements, such as the collision of neutron stars
Yes.
and things like that, which makes me think, particularly when they refer to gold. And so, does anyone here have any gold in your possession or in your teeth or in your jewelry? And that means you're carrying around possibly the collision of neutron stars, which is a truly astounding kind of event.
Yeah, they're all into Bitcoin.
Yeah,
John,
okay, well, we'll take your useless gold then.
all right. So we'll move on. All right. So this is an astronomy diagram. It's a little bit confusing. So this is the age of the star, right? Nothing can be older than 13.8 billion. So this is one that formed yesterday. And this is Z over H. So Z is metal, H is hydrogen. So it's basically the log 10 of the abundance of the metal. So this would be a star that you had as much metal in it as hydrogen. And there aren't any like that, but there's some that get pretty damn close. And, it's only a 3.5 log cycles, so it's not a big range. But what you can see is old stars contain less metal, young stars contain more metal. Does anybody have an opinion why that's true? Anybody got an idea? Oh, John?
Well, I guess the stars start off as all metal with hydrogen and helium are 50%. And then as you create carbon and boron and all the other ones, you're creating non-metals.
No, the older the star, the less time they've had to go through those processes that we were just discussing. So young stars, they scavenge material from other supernovas. And like our star is definitely did not form after the Big Bang. The Big Bang was 13.8 billion years ago, but our sun started 4.5 billion years ago. So how many cycles of stars have been doing their thing before the sun started? But the younger stars have access to the remains to recycle the material from older stars that are blown up. Does that make sense? And Andrew, Andrew had his hand up, but did you take it down or?
Yeah, I took it down. I was just gonna say because they might burn hotter initially, but or they might be able to do more fusion because they have more fuel to begin with.
No, that's not that could be very well part of it, but in general, the explanation is that the younger stars have got more of this pre-processed material to work with, and the older stars don't. So, you think about would Earth have been possible, 100 million years after the Big Bang? And the answer is probably not, because the elements that make us up, we've got a hell of a lot of elements in our personal bodies didn't exist. So, it took a while for that evolution of the elements to happen. That is an evolution, more metals being produced with time because more stars are processing multiple episodes of previous star remains. Sort of universal recycling, if you like that term. All right, so how did all the elements, however they formed, get to the Earth? So, Earth accreted from a hot gas cloud on the outer limb of the Milky Way about 4.5 billion years ago, and this nebula, the hot gas cloud is the nebula. This nebula contained material from any number of sources, including a recent supernova. And we know that the Earth, that the solar system accreted from the material of a previous supernova very quickly after that supernova, because we've got material that could only be produced that way in the early solar system materials of meteorites. All right, so this is basically how the solar system formed: a collapse of a interstellar molecular cloud under gravity, dominated by hydrogen and helium. That collapses and starts to rotate. This is sort of a circumstellar disk. Most of the mass goes into the middle, which becomes the sun. And then slowly, from this rotating gaseous hot material, the elements start to, matter starts to condense from gas to solids. And, this material coalesces in various ways, and various lanes are scooped out by bodies that are forming in these lanes. And we end up with sort of the regular system of our solar system. So that's how we got here in a nutshell, and how the elements that are in our planet got here in a nutshell. So this is sort of a artist's impression of what the solar nebula looked like 4.56 billion years ago. The sun and all of this matter rotating around there, just waiting to turn into planets and people. So there we see it again. So the interesting fact is the mass in this coalescing, collapsing molecular cloud is concentrated at the center. 99.9% of it, or 99.86%, is concentrated in the center, and the rest of the 0.14% is everything else, including the Earth. So now, how do we understand the bulk composition of the Earth? Because the Earth is differentiated. We know this from geophysics and geochemistry. We all know about the inner and the outer core, the mantle, the crust, the oceanic crust, the continental crust. We say that the Earth is differentiated, and that has. And as it turns out, each of these elements, each of these layers has its own affinity for different elements in ways that kind of complicated our search for elements we want. So we can't determine the bulk composition of the Earth directly from any sample that we collect at the surface. We certainly can determine the composition of the crust, and that's pretty damn useful. But in order to estimate the bulk composition of the Earth, we need to understand the composition of the solar nebula. And how do we do that? Well, we study the sun and the meteorites. And let's see what the next one is. So one of the things we can do is look at the solar photosphere. So we can use spectroscopy to analyze its composition. The sun is very hot and is well mixed as a result of intense convection. Therefore, the outer part of the sun, the part we see, is a pretty good sample of the bulk sun. And that's the photosphere, which is the visible surface of the sun. And we can determine the composition of the sun from analyzing its spectrum.
Hey Bob, I was gonna ask real quickly.
Sure.
You said so all the metals were created on Earth from the Big Bang. Does that mean that there's a finite number of each individual
No.
metal?
What you said is incorrect. The metals were created by processes since the Big Bang.
Okay, excuse me.
So, but your second part of your question is that mean there's a finite abundance of metals? And yes, there is, right? There's a finite abundance of mass in the Earth, and so that mass is made up of different elements. So there must also be a finite abundance of those elements in the Earth, right? I mean, there's two kinds of way to think about it. You know, mathematically, it's finite. In terms of our ability to exploit it and use it, it's essentially infinite, as we will see, because it's a matter of economics. The exploitable things, the things that are going to be exploited, are the things that people can make money on, either as a result of selling them directly or as a result of government subsidies or tax benefits or something that makes their spreadsheet look in the black rather than in the red. Does that make sense?
Mm-hmm. Yeah.
I have the same opinion about oil and gas. People say we're going to run out of oil and gas. And the answer is no, I don't think we will. What we're going to run out of is cheap oil and gas, because if people want oil and gas and they're willing to pay $100 a gallon for gas, we'll find more. I mean, there's a lot of oil where it's just not economic to produce it, because you've got to make money in order to stay in business, right?
Mhm.
And it becomes, maybe you think that's a semantic argument, but in the world of economic geology, remember the word number one is economic, which means don't do it if you can't turn a profit. That's what economic means. It's like, why would you do something if there's no money to be made? You can't support anybody, yourself or anybody else. All right, so let's keep going. That's a good question. So how do we know what the composition of the sun is? And here we're looking at spectroscopy, and we're looking at the wavelengths of light, right? Shorter wavelengths are purple and longer wavelengths are red, and this extends visible, right? The ultraviolet and X-rays are down here, and infrared and radar are up here. This is what our electromagnetic sensing organs called eyes can detect. And just within that part of the spectrum, there are lines. So this is an absorption spectra, which means the elements in this material are absorbing energy of exactly that wavelength, right? So those dark lines in the spectrum indicate elements in the upper photosphere that absorb the outgoing light. And in contrast, there are emission spectra, which is hot gases in the chromosphere emit their own light. So these are different parts of the sun. The chromosphere is below the photosphere. We're not going to get into the details, but the point is it's spectroscopy that gives us the information about what the sun is made out of. But of course, who would trust an astronomer, right? I certainly don't. So we want to trust and verify. But here's what we see. So this is a very interesting diagram, not only because we're looking at 15 log scales, 15 orders of magnitude on the vertical axis, and the entire periodic table, right? Element 92, uranium. And you're going, okay, what is that? So you look at this plot, solar system abundance, log 10 atoms of elements per million atoms of silicon. That's an interesting unit, an interesting way to frame this. But let's see what we're doing. So there's silicon, and it's right there at 6, which corresponds to 10 to the 6 or a million. And so everything is sort of normalized to that, to silicon being 10 to the 6, which means hydrogen is 10 to the 10.5, which is 4.5 log units more abundant in the solar photosphere than silicon. Okay, that's not a surprise. We know the sun is made out of hydrogen, and there's an order of magnitude less helium than hydrogen in the sun. Okay, but look at lithium, beryllium, and boron. They're pretty scarce in terms of the solar photosphere. I mean, orders of magnitude scarcer than the adjacent elements of helium and carbon, many orders of magnitude. So you can see the sun is 73% hydrogen, 25% helium, and everything else is 2% of the sun. Everything here. Okay, so we're not going to look way too much on there, but do you understand what this diagram means? How to read this diagram? Has anybody got any questions about it? It's one of my favorite XY plots, and I don't have a lot of favorite XY plots. Yes. Yes, Clint.
Yes, because I do have a question, which is like, it goes, you don't hardly ever see elements going, carbon, nitrogen, oxygen, even. It's up, down, up, down, up, down, up, down. And the variety of, how far it goes up or down changes, but each next one is either up or down.
Yep. I'm going to explain that, but thank you for noticing that. Okay. So how do we know that the sun and all the planets, et cetera, formed 4.56 billion years ago? That's the kind of thing that geology students are told over and over again, And the answer is because there's strong evidence from what we call primitive, undifferentiated meteorites, which we call carbonaceous chondrites, that link the solar nebula to the bulk composition of the Earth. So the way that we think about carbonaceous chondrites and the origin of the solar system is that the hot solar nebula cooled and carbonaceous chondrites formed from the condensing matter. And these are called primitive meteorites, and they are thought to preserve the original composition of the solar nebula, excluding, of course, the gases, hydrogen, helium, and some other gases. But it is thought that something like carbonaceous chondrites aggregated to form the Earth and the other planets. And we can date them and get the age of the solar system. So let's watch a video.
Hi, I'm Celine Shaw from King Edward's in Edgbaston, and I'm here for a week on work experience. I've chosen this Allende meteorite, this small fragment, for the object of the month. It was the largest carbonaceous chondrite ever found on Earth, roughly the size of a car, and it was spotted a giant fireball falling over the Mexican state of Chihuahua on the 8th of February of 1969. As it exploded, it scattered into thousands of fusion-crusted individuals. As you can see, there's the fusion crust here. It's got like a glossy finish, and this would have formed because as the fibre was falling, it was falling at great speeds, say about 10 miles per second, and this would have produced a lot of heat and melted the exterior. As it exploded, it was dispersed over quite a large area, and there was an extensive search for all the pieces. It was actually described as the most studied meteorite in all of history. It was important for research purposes because of its rarity, as it accounts for less than 5% of all the chondrites on Earth. And also, inside, there's lots of calcium-rich inclusions, which are among the oldest objects in the solar system. And unlike other chondrites, it doesn't include any iron or nickel, so it's quite unusual from that aspect. This chondrite would have been formed in the solar system a few million years ago, and it would have been formed by the accumulation of dust and grit particles all clumping together. And as you can see, in the internal structure, as it's been cut and polished, it's more visible. There's some dark chondrules and also some white-coloured calcium and magnesium-rich inclusions. And also there's some smaller millimetre-sized chondrules, which are only found in meteorites, not in earth rock.
Yeah, so that is, this isn't a course on meteorites, but and one thing that I disagree with, which is that it formed from the solar nebula a few million years ago. I think she meant a few billion. Well, in Britain, they have a different definition for billions. It would be a few million in Britain because they don't really, to them, a billion is a million. To us, a billion is 1,000 million. But so be careful using billions around British people because it'll confuse them. All right. So we've got these two things. We got the solar photosphere and we've got carbonaceous chondrites, the Allende meteorite, and we compare their abundances. And that's what this diagram does. Only 9 orders of magnitude. And, obviously helium and hydrogen are off the scale. But for most of these elements, all the ones we're interested in, it pretty much lines up, right? The abundance in the Allende meteorite, I think this is parts per million, but I don't know. No, that can't be right. Because magnesium, silicon, and iron are most abundant. Oh, 10 to the 7. I thought it was a -7. Yeah, so the correspondence makes us think that we're actually right, that the abundance of elements in the solar photosphere is the same as the abundance of those elements with the exception of the gases in the carbonaceous chondrites. And it is that carbonaceous chondrite material that accreted to form the Earth. So you'll see occasionally rare earth patterns that normalize things to chondrite, and that's why it's thought that chondrites represent the bulk Earth. All right, so this is the relative abundance of elements in carbonaceous chondrites in the solar photosphere. It's the bulk composition of the Earth. These elements are concentrated in different parts of the Earth because the Earth differentiated. So there's 3 interesting things about this diagram. One is the declining abundances from left to right, from light to heavy, and that's because of the processes of the way the elements form. I mean, iron is sort of the peak of things that are formed by inside star processes, and anything beyond that has to be formed by special creation. So this difference that happens at iron and the iron peak makes sense from that perspective. Second, the even numbered elements are significantly more, up to 2 orders of magnitude more abundant than adjacent odd numbered elements, as Clint pointed out. So carbon is higher than nitrogen, oxygen is higher than nitrogen and fluorine. Carbon is an even numbered element, oxygen is. All of these peaks are even numbered elements, and they are all more abundant than the adjacent odd numbered elements. And then, of course, this depletion of the light elements, lithium, boron, and beryllium, that we've already talked about. So what's going on? So the abundances, solar abundances of the elements decline from left to right because of the relative importance of element forming processes in the universe. Lots and lots of hydrogen, helium from the Big Bang. The elements up to iron are made in large stars over the last 18 billion years that the universe has existed. And there's much less of the elements heavier than iron because these are only really made in supernova and neutron stars colliding and a few special processes that aren't as common as the previous ones. So that explains the overall decrease from light to heavy. Now, why are the even numbered elements significantly more abundant than the odd number of elements? Well, it's because of the Otto-Harkins rule. And this is interesting. ChatGPT, I asked for a picture of Giuseppe Otto, and this is what ChatGPT gave me. I don't think it's a photograph. I was able to find a photograph of W.D. Harkins. So the Otto-Harkins rule holds that an element with an even atomic number, Z, is significantly more abundant in the solar photosphere and carbonaceous chondrites, and therefore in the bulk Earth, than elements with immediately adjacent atomic numbers. So for example, sulfur, Z of 16, is more abundant than phosphorus, Z of 15, and chlorine, Z of 17. So generally speaking, the relative abundance of an even-numbered element is roughly 2 orders of magnitude greater than the relative abundance of the immediately adjacent odd-numbered element. Okay? So, okay, that makes you go, okay, so we got lots of the even-numbered elements and not so many of the odd numbers. Not true, because the chemistry that Matt's going to start talking about very soon throws all of this into a cocked hat. The elements get distributed once they're in the Earth by a number of processes that we'll be talking about over this course. So finally, why is the solar photosphere carbonaceous chondrite and therefore the bulk Earth depleted in the light metals, lithium, beryllium, and boron? It's because they're not produced in normal star processes. They're only produced by interaction of solids with cosmic rays. And that's a much less important nucleosynthetic process than, things going on in stars.
Oh, wait.
Question?
Yes, a previous slide that says, why are even-numbered elements significantly more abundant? And you said the answer is because, but that's as far as you get. You don't actually explain why.
Oh, you wanted me to explain why even-numbered elements are more stable than odd-numbered
Unless it would
elements?
take a week, in which case keep going.
It is an excellent question. It's got to do with nuclear stability, and I've just told you more than I know.
Okay, good. Carry on.
But it's a really good question, You do please remember, this is an introductory course. All right, now that we understand the bulk composition of the Earth, how does that help us find mineral deposits? And the answer is, it doesn't. Well, it does, because don't look for any elements or deposits made up of elements heavier than 92, because they didn't get produced. But, just knowing what's available in the Earth doesn't tell you what's within reach of us, surface living creatures. So, for example, you might say, "Oh my God, lithium, beryllium, and boron, we have no chance." But fortunately for us, the chemistry of those elements is such that they tend to migrate towards the surface. The differentiation of the Earth and the processes that have happened since then allow them to be concentrated. So, in exploring for lithium, beryllium, and boron, nobody says don't bother because there's not enough of it created by the stars. It's these other considerations, like what concentrates elements towards the surface, become much more important. But okay. Now here's the key thing: is we can only access the top 10 kilometers of the Earth directly. So I say that because the Soviets drilled a drill hole down to 11 kilometers on the Kola Peninsula. So we know we can go that deep. Now they had to abandon it because it was too hot. And obviously that's not an economic way to mine, but nobody's ever been able to drill deeper than 11 kilometers. And I doubt that anybody's going to try in our lifetimes. So we're kind of stuck with the outermost little bit. Fortunately, that's not a bad place to look. All right, now these are the relative abundances on Earth's surface. This is a periodic table. And what you can see is it bears, other than the organization, it bears very little resemblance to anything we've shown you now, right? There's a lot of hydrogen. The hydrogen is in water, right? And in various hydroxyl minerals. The helium has not much of that. Boron, a lot of carbon, nitrogen, oxygen. Yeah, a lot of oxygen at the surface. That's the single most abundant element near the surface. So you can see that as we go down here into the rare earths and these things, that you can start to see the outlines of that sawtooth declining pattern. That diagram should have a name, which I don't have, but you know which one I'm talking about. You can start to see the elements like that, right, in here. But look at iron. It's much more abundant than manganese or cobalt. Much more abundant than ruthenium, osmium. Look how small that is. So this is more the way that an economic geologist would look at the composition of the earth, because that's what we can access, near the surface. All right, now let's try and understand better how these things are distributed in the top few kilometers of the earth. So we need to learn about Goldschmidt and how he grouped the elements. So Victor Moritz Goldschmidt, handsome dude there, full head of hair, obviously young man. He was a Norwegian geoscientist. Oops, sorry. He was a Norwegian geoscientist who worked with Vladimir Vernadsky, who was a really talented, remarkable Ukrainian geochemist, to be the founder of modern geochemistry and crystal chemistry. And we celebrate his life every year with the Goldschmidt Conference, which this year was in Prague. I think Matt went to it, got some kind of a disease. And then this is, anytime you show a picture of a person with Einstein, they're important, right? Because Einstein's kind of like God. We have no idea what he was telling him about rocks or why they went out in their fancy clothes. But
I think they're having a fight. This is the famous Goldschmidt-Einstein fight.
Well, Einstein has the advantage of topography, that's for sure.
He's a bigger dude than I thought, too.
Okay, so we're going to learn about Goldschmidt's rules, Goldschmidt's classification of the elements. We'll learn about Goldschmidt again in another lecture. So he broke out 4 different groups of elements, not by their abundance in the solar photosphere, not by their abundance in meteorites, but just how they behaved in the Earth. So, and there's another element group that we could put in there, the biophile elements that make up us, but we're geologists, so we won't. So let's talk about lithophile elements, siderophile elements, chalcophile elements, and atmophile elements. We can dismiss atmophile elements. Those are just the gases. And let's concentrate on the lithophiles, siderophiles, and chalcophiles. These are terms we'll use a lot in this class because they simplify matters to a certain extent. So lithophile elements are rock-forming elements that are partitioned into silicate earth. That is, these are elements that like to bond with silicon and oxygen, like magnesium and lithium and things like that. Siderophile elements they like to appear as metals, so they follow metallic iron and nickel into the core. And chalcophile elements, those form sulfides. Now, you don't think it's that simple, because there's plenty of iron that behaves like a lithophile. There's plenty of iron most of the iron behaves like a siderophile, and there's plenty of iron that behaves like a chalcophile. So it's more complicated than just the way he pitches it. But potassium is purely lithophile. Copper behaves as a very chalcophile element, and most of the metals do as well. But we're going to learn more about the behavior of specific elements in ore deposits as we talk here. Any questions on this interesting material, which probably will be on the midterm? I'm sure it's on the study guide. Whatever's in the study guide will be on the midterm, or is game. So lithophile elements partition into silicates like granite and basalt, and the minerals that make these. There's granite, there's basalt. Very up-to-date penny for scale there. What is that? 18 something. Chalcophile elements, these partition into sulfides, pyrite, chalcopyrite, galena, sphalerite. This is of great interest to this class. And siderophile elements follow metallic iron into the core. So what we're looking at here is an iron meteorite, very different than the Allende carbonaceous chondrite. And you're seeing an exsolution pattern of two iron phases to make that pattern. It's called a Widmanstätten pattern. Exsolution of nickel-rich and nickel-poor iron in a cooling iron-rich core of an asteroid parent body. And a lot of what we think we know about Earth's core comes from studying these kinds of meteorites. But these are both in siderophile. All right, and this gives us a chance to estimate the composition of the Earth's outer core. You can see it's mostly iron, quite a bit of nickel. People argue about how much sulfur and oxygen is in there. But basically 33% of Earth's mass is in the core, dominated by siderophile elements. Now, we can also take these and talk about how these elements behave in melts and fluids. So we're going to talk a lot about fluids and a little bit about melts. But in these processes, it's useful to talk about compatibility of elements. And compatibility means the likelihood that it's going to go to a certain mineral. So let's think about the petrogenesis of basalt. So when you partially melt Earth's mantle to make a basalt, the elements that are concentrated in the melt tend to be the incompatible elements. They're excluded from minerals. It's like, when you're cleaning house, a partial melting episode is a lot like cleaning out your garage. You're going to get rid of the stuff you don't want. And those are the incompatible elements. So they'll go into the melt phase. So things like potassium, sodium, rubidium, uranium, thorium, lead, those things are very incompatible in the mantle, and they tend to get concentrated in melts. Melts rise to the surface, make the continental crust. That's where we find our ore deposits. So in many ways, we're looking for incompatible elements that were transported from some source. Matt's going to talk about mineralization systems where this will be important. And they contrast with compatible elements, which is like, you're cleaning out your garage, but you have a car in there. You're going, I'm not throwing that away. That would be a compatible element. You might move the car, but the point is the mantle says, I'm gonna hold on to magnesium and nickel and those things, and I'll kick the potassium and rubidium out. So we can talk about compatible versus incompatible elements. And it depends on the system how an element behaves in many cases. But this is a terminology we'll use. So I just wanted you to be slightly familiar with it. All right. Now, the abundance of oxygen we're going to find is a really important process control on ore deposits. So here we're looking at an exposed ore body. So we've got really complicated relationships here. Here's the surface exposure. This is an exposed ore body. Probably there's trees and grass and stuff on it. And what we've got here is the primary ore at depth below the water table. I don't like the way they've drawn the water table because and then there's a zone of secondary sulfide enrichment. So this primary ore is a sulfide ore, right? But sulfur will combine with oxygen to make sulfuric acid, and that's an environmental problem. You have drainage from mines where the sulfides have been exposed to the atmosphere, and it starts to generate sulfuric acid, kills all the fish, everybody's screaming. Okay, so up here at the top you have the zone of leaching, which is it's raining up here and the water is circulating. You've got tree roots. There's all kinds of things going up here, chemical processes, but they're all involving oxygen and water, right? And then below that, you've got a zone of oxidation where the atmospheric oxygen can still get in here and react. And then down here, You have the zone of secondary sulfide, and here's the primary ore. So we're going to talk about oxygen fugacity, and Matt's going to talk about that in some detail. So if there's a little bit of oxygen, we've got a low oxygen fugacity. So if we have low oxygen fugacity, the iron is going to be reduced to iron. That little zero means it's metal. It's going to behave as a siderophile, metallic iron like in Earth's core. The sulfur is going to be reduced and it will make sulfide minerals as opposed to sulfates. Sulfates, that's a confusing terminology you'll learn more about. And the carbon will be reduced either as graphite or diamond, depending on various things. If we go to a high oxygen fugacity, the iron is going to be oxidized to ferric, iron +3. The sulfur will make sulfides, SO4, right? You're going to have a completely different iron and sulfur chemistry. And moderate oxygen fugacity, the iron will be ferrous, Fe+2. The sulfur will tend to be sulfides, etc. So the way that ores appear on the Earth's surface really are influenced by this interaction in what we could call the critical zone, but is actually the zone of exploration from our point of view. All right, so if we think about oxygen fugacity in the Earth as a function of depth, this scale here is ridiculous, right? Atmosphere to the core. But, the core has got a very low oxygen fugacity. The iron is metallic iron, and so that's very low oxygen fugacity, and iron's behaving as a siderophile. Up in the atmosphere, where we got, what do we have? Is it 23 or 26% oxygen? It's a lot. That mixes with the ocean. The ocean can have slightly lower oxygen fugacity at depth, depending on a number of things. And then we got this critical zone, which is usually referred to now as soil. When you say critical zone, now most people will think of what's going on in the soil. But if you think about what's going on here, this is kind of a critical zone too for what's happening to ore deposits. It's this transition from in the case of ore, it's the transition from high oxygen fugacity at the surface to low oxygen fugacity at depth. And then as you keep deeper, the fugacity decreases and decreases. So the good news for us is the mineralized zone for so many elements is concentrated near the surface because of this interaction between sulfides and oxygen. And we're going to talk a lot about that, but minerals are composition form, how they occur in nature. A mineral is a naturally occurring inorganic solid with a definite chemical composition and crystalline structure. That's a really good midterm question, by the way. May contain metals, but is generally not pure metal. So examples of minerals would be hematite, Fe2O3, bauxite. That's kind of a complicated mineral. Probably the single most recognizable mineral on the planet. Whereas a metal is a pure element or an alloy with specific properties, shiny, conductive, malleable, and it is extracted from minerals, which for the purpose of this class, minerals and ores,